So what this self-organizing map does is, in this equation, basically, it takes this Taylor series expansion of this equation. If you do the Taylor series expansion of this, what you'll get is that equation written there. So this is my Taylor series expansion of this equation, where this is my angle node, this is the inverse Jacobian, and this is the motion in the interface. So how did we get this? Basically, I know this equation for any robot manipulator or a robot system. I want incremental change in joint velocities, for which I need to take the inverse of this, which is this. So in this case, what I do is, this fellow is my matrix A, which is given there, a lambda. So what the learning basically does is, it tries to learn the relationship between this and that. That's what it is doing. So what it is estimating, whether it's neural net or support vector or whatever, it is estimating this inverse Jacobian. It is learning the inverse Jacobian. And once it has learned, the advantage being, it can be done in real time. So you give any input, it will give you the output in real time. That is the advantage of this. Now, self-organizing map is a little different from normal neural nets. Okay, so what it is doing here, okay, so what it is doing here is that it is estimating this Jacobian, inverse Jacobian, right? And how it is doing that, we are giving it sets of joint angles, and for that joint angle, it is estimating that and is figuring out this one. So essentially what we are doing is, we have an input space and we have an output space. This is my robot system. And yeah, so these are my thetas here, and that's my E. So how do we teach it? So what we are teaching it is, we generate different thetas randomly. And from forward kinematics, I know that for this thetas, that is my vector position. Then we generate another set of thetas randomly. And for those thetas, I can compute from forward kinematics what is the corresponding E. Right? So by doing that for very large number, we can basically find the relationship between that and that. And that is estimating the inverse Jacobian. Right? So we are estimating the inverse Jacobian by this relationship by teaching it. So when we are teaching it, okay, so how this network actually works is, what is done is, the input space is this, right? I want the intervector position x, y, z. So it's x, y, and z. So I divide my x, y, z axis into 9 sectors each. That means I simply take my x-axis, break it up into 9 parts, y-axis 9 parts, z-axis 9 parts. And with each of the parts, I make a region in space. And then in that region in space, I see for that region in space, what is the corresponding region in space here. So this is input space, that's output space, which are broken up into small, small sectors. Now, why this is done, this is what is the property of self-organizing. This is a little bit different from other neural nets. So when I'm teaching, I'm breaking this up into small sectors. For that corresponding region, I'm seeing what is the corresponding region on that side. That is what it is learning. So it is learning a J inverse Jacobian for each region now. Small, small region, this region to that region. Now what is the advantage of this? What would happen is, instead of learning everything in one shot, it can identify one region here with another region there, and that is what is called self-organizing. So in different solution space, some solutions from here will remain in some solutions here, and the regions can be correlated. Right? So the search becomes faster. So when you're giving some input, it knows which region it was, and it gets the corresponding region on this side. It doesn't have to search everywhere. Right? So it makes it very, very fast, and this is what is called self-organizing. Now the other advantage being that the redundancy resolution ensures, talk about this. The redundancy resolution ensures that all the solutions are preserved. So for every point here, if it's 14 degrees of freedom, there are going to be infinite solutions. Okay? So what it will do is, it will keep some solutions based on what is the criteria you have set. So in our case, we have set the criteria of manipulation ability. So we have put a weight matrix, minimum angle node, and manipulation ability. So this is my training data. And training data essentially means randomly generating this, getting that, correlating the regions, and getting the weight vectors. So, what is the constraint? The constraint here is that we have two parts. We have a robot and we have an arm. So the way we have formulated the problem in terms of the constraints, we have said that the arm should move such that the manipulation ability is maximized, and it should be always more than 0.7. Okay? So the arm is going to move to maximize manipulation ability. If that cannot be done, then the robot will move, because there are two parts in the problem. So by doing that, we ensure that the solutions are found such that, yeah, so this is our input-output. This is again topology. This word topology keeps coming back, because essentially we are mapping from the input space to the output space, and the spaces have different structure. They are not the normal partition spaces. So if you look at the joint angle vectors, we are covering all of them, whereas in the output vectors, what is happening, they are getting clustered. So they are getting self-organized. So this is our learning, our teaching. We are generating the thetas randomly, and for every theta we are generating what is the end effector point, and then teaching that corresponding end effector point. So what you can look here is that this is covering the full space, whereas here they are getting clustered. The solution clusters appear to lie here in particular cases, and this depends on the terrain. Okay, so by doing this, we try to look at finding the inverse kinematic solution for different trajectories. For example, straight line here. So if the end effector has to follow a straight line, the end effector is moving and the robot is also moving. So both of them are moving together such that the manipulation ability is being maximized. This is in the case of a bumpy terrain that is following a straight line with a bumpy kind of terrain. So it is able to resolve the redundancy in real time. The advantage being it's in real time. This is for a bumpy curved terrain. So all kinds of this has a bump in there, then this is an inclination in here, and you want the end effector to follow this kind of trajectory. So the robot and the manipulator are moving such that it can follow the trajectory and also resolve the redundancy. So these are all different kinds of surfaces that were tried out, and then we move to the real experimental part, where we have taught the robot to follow a trajectory using the K-SOM network. In order to track it, we have put a kinet on top, kinet sensor which can see what it is following, and then we have both of these are integrated with the computer so we can track it. Now, this brings us to a very interesting question here, that whatever robotics we are applying here, like we were talking of frames, we are doing forward kinematics, inverse kinematics. Do we really know the frames? See, if you don't know what's a local frame, you don't know what's a global frame, then there is no question of a frame. All your kinematics is not valid, right? So if you're looking at the moon or you're looking at an unstructured environment where you don't know, you actually do not know the frames. We can put a global frame somewhere here and say this is my global frame, and then this is my local frame. But what is the relation between global and local? Now you need to get somewhere else and see this global and the local and then say this is my matrix, right? Which is very difficult actually. And in the process of trying to do that, a lot of errors will come. So this has given rise to the next area of robotics, which is supposed to be the future trends in robotics called probabilistic motion planning. So we don't say that whatever we are doing is deterministic, but we add some probability into that and say, okay, I know this is here, but it's not exactly there, but it could be somewhere in there, because there is a lot of error in the system. So when I show the experiment for this, it will become clear. So essentially we carried out different experiments, and in order to track, what we basically did is we put this circular balls of different colors. You can see on the top, the 4 balls are there, and you can track this using a kinet sensor. Once you get the kinet sensor, from here you can do the forward transformation and go to there by using forward transformations. So essentially, if you know this tree, we know where the fellow is also. Okay, that's how you track it. So let's look at actually what happens. So we are given end effector trajectory which we are supposed to follow by doing redundancy resolution. And this is a flat terrain, and the path is a curved path. And we are tracking. So when you're tracking, you see what it does. So there is some error coming in there now. So how would you estimate this error? What is the error like? On flat terrain, there's not much error. But once it starts going on uneven terrain, and it starts turning, then we find that the error is pretty high. And the end effective trajectory can go off by centimeters now. It's not that our model is not right, it's not that, it's just that all the parameters that we saw, turning, sinking, slipping, these have not been considered, and you cannot consider them, it's not possible, right? So we have to add some kind of probability in our motion planning now. So whatever deterministic models we have built, if we can add some kind of sensor noise and add some probability distribution on that, maybe we can have a better estimate of the system. So in terms of research, the next area of research apparently is probabilistic motion planning, where they add probability distributions into the system and then proceed from motion planning. Okay, so today I think I have run out of time. So I'll stop here. So I hope I've been able to explain some aspects of motion planning in 2D and 3D. So if you have any questions, we can discuss it later, or you can refer to the papers. Okay, thank you. So questions, we can have it after, during lunch or something.